So let's talk about an idea that's, well, simple, but also pretty profound. When it comes to energy, it turns out the journey is just as important as the destination. We're going to see how this one single principle powers everything from our cars to our power grid. Honestly, understanding it might just change the way you see the world.
So let me ask you this. What does a car engine, a giant power plant, and even your own lungs have in common? Sounds like a riddle, right? Well, the answer is all about thermodynamics. They are all systems that have figured out how to harness work and heat to, make things happen. Okay, so here's our game plan for today. We're going to start with the basics. What in the world is thermodynamic work? Then we'll make it visual, see what it actually looks like. And that's going to lead us to the main event, why the path matters so much. We'll also meet work's famous partner, heat. And finally, we'll connect all the dots and see how this stuff is working all around us, every single day. All right, first things first. Before we can really dig into work, we have to get our terms straight. We need to know what we're talking about. So, in thermodynamics, the thing we're interested in, we call it a system. Now, don't let that word sound all complicated. It's really just a fancy way of saying the specific thing we're focusing on. It could be the gas inside a piston, the steam in a turbine, or literally the air you just breathed into your lungs. So this gives us the whole picture. You've got your system, right? Everything else, the entire universe outside of that, is just called the surroundings. And that line separating them, that's the boundary. And here's the key takeaway. For things like work or heat to happen, energy has to actually cross that boundary. Okay, now for the official textbook definition of work. And I'm going to warn you, it's a little weird at first. Thermodynamic work is an energy transfer where the only thing that happens outside the system could be the raising of a weight. I know, that sounds super abstract. So let's look at a picture that makes it all clear. And this is what makes that strange definition finally click. Look at the top image. Our system is the battery and motor, and it's spinning a fan. That's doing a bunch of stuff to the surroundings, right? It's moving air, making noise. But look at the bottom. We swapped the fan for a simple pulley. Now the only thing our system is doing to the outside world is lifting that weight. That right there, that is the pure distilled essence of thermodynamic work. So the whole lifting a weight idea is a great start. But to really get a handle on this, we need a way to see it, to measure it. So how can we turn this kind of abstract concept into something we can actually look at on a graph? Let's use a classic example. On the left, you've got some gas in a cylinder, pushing a piston from position 1 to position 2. It's expanding, it's doing work. And on the right, you can see that exact same process, but now it's drawn on a graph. We've got pressure going up and volume going across. That curve shows us exactly what happened. And here it is. This is the big aha moment. You see that shaded area under the line on the graph? That's not just some random shape. That is the exact amount of work that the gas did when it expanded. It's that simple. If you can figure out that area, you know exactly how much work was done. It's an incredibly powerful idea. Okay, now that we've got this whole area under the curve thing down, we're ready for the main event. This is the key insight to this entire explainer. So this begs a really important question, doesn't it? If we start at the same place, state 1, and we end at the same place, state 2, does that mean we always get the same amount of work done, no matter how we get there? All right, let's say we travel from state 1 to state 2, and we take this route. We'll call it path A. Just like we learned, the work we get is that shaded area underneath. Got it? Okay, lock that picture in your head. But what if we try a different way? We're starting at the same spot, ending at the same spot, but this time we're following path B. I mean, you don't have to be a math whiz to see it, right? The area under this curve is way smaller. That means we got less work out of our system, even though the start and end points were identical. And just to really drive the point home, check out path C. Same start, same finish. But by taking this path, this high road, we've made the biggest area yet. We squeezed the most possible work out of the system. And this leads us to the absolute crucial insight. Work is path dependent. The journey you take literally determines the outcome. And what this all boils down to is a really deep concept. You can't say a system has a certain amount of work inside it, the same way it has a temperature or a mass. Work isn't a property. It's not something you own. It's something you do. It's energy in transit, crossing that boundary. But work isn't the only way energy gets across that boundary. It's not the only game in town. So it's time to meet the other side of the energy coin: heat.
Okay, after that tricky definition of work, you'll be happy to know that heat is way more straightforward. We all get this intuitively. It's just energy on the move because of a temperature difference. You put a hot coffee mug on a cold table, energy flows from the mug to the table. That flow? That's heat. Simple as that. Now here's where it gets really interesting. Look how similar these two are. They're both energy in transit, energy on the move. They both have to cross a system's boundary, and, this is the big one for our story, heat is also path-dependent, just like work.
It's actually a really beautiful parallel when you think about it. Just like work is the area under the curve on a pressure-volume graph, you can visualize heat as the area under the curve on a different type of graph, usually one that involves temperature. The same elegant visual logic works for both.
Okay, that's a lot of theory, I know. So what? Why should you care about any of this? Well, because this idea of path dependence isn't just some abstract curiosity. It's the core principle that makes our modern world run. I mean, this is what engineers do all day. They design machines that are incredibly clever at manipulating these paths. A pump or compressor, like you see on the left, is designed to follow a path that uses the least amount of work in to get the job done. But a turbine or an engine on the right, it's the total opposite. It's designed to follow a path that gets the absolute most work out. And that brings us right back where we started, the car engine. An engine cycle is basically just a closed loop on one of these pressure-volume graphs. The engine follows one path to compress the gas, and then it forces a different, higher path on the way back down. And the area inside that loop, that is the net, useful work you get out of every single stroke of the piston. The whole point of engine design is to make that little loop as fat as possible. So we've seen that in the world of machines and energy, the destination is not the whole story. The path you take is what actually defines the outcome. And that kind of makes you wonder, doesn't it? Where else in life is the journey more important than the destination? Where else is the final result defined not just by where you start and end, but by the specific path you chose to get there?